Welcome back to ECE 442-542. You have spring break coming up next week, and maybe in celebration of that, I don't have office hours. I actually have another meeting that day. So if that impacts you in any way, let me know, and we'll try to work around that no office hours this Friday. Homework number 4 is due the Monday that you get back. And I don't know how many of you have logged into D2L consistently, but you now have 2 more lectures since we last met that are now posted. Yes. The question was really? And the answer was yes. So the last time we met, we had lecture 4.1. Now there's a lecture 4.2 that goes over the zero order hold equivalent of an integrator. We talked about the zero order hold equivalent of a pure mass and of a pure gain. And this is sort of in between those. And it also, lecture 4.2 talks about or provides a table of those zero order hold equivalents for particular systems. The gain, the integrator, the pure mass, and a first order system. So it's a PDF file with a video. So I went ahead and recorded that yesterday. So you can watch that at your leisure. But then there's another one, lecture 4.3, which talks about doing the zero order hold equivalent for state space representations. And that we haven't talked about. And that's what will help you on problem number 2 on homework assignment number 4. Then exam number 2 is in 2 weeks. Do I have the right dates? That will be the 14th of March, 3.14, if that means anything to you. So on Pi Day, we have exam number 2. And for those of you that have been anxiously trying to determine what you wanted to do for a project, I've now provided a project description on the website, but that's only concerning the students in the 542 section. If you're in the 442 section, you don't have to worry about doing a project. Today, what I want to do is actually move into the next scenario of performing discrete equivalents. The last time we looked at scenario 2, which was where we had a hold preceding our transfer function, and we incorporated that hold's behavior into the dynamics of G of Z. Today, we're not worrying about preceding our transfer function with anything. We're just wanting a sort of a direct discrete equivalent from a given transfer function, D of S or C of S, to its discrete time equivalent, which we're calling C of Z. And we'll work through many different ways. We'll do numerical integration, which conceptually is not difficult in terms of how do you find the G of Z. You simply start with a G of S, and depending on which of these numerical integration approaches you want to use, you simply replace every S with the appropriate argument that involves Z and maybe a capital T. We'll go through where those come from in this lecture. But we have the forward integration technique, the backward integration technique, and a trapezoidal technique or a bilinear numerical integration approach. And we also, I don't know if we'll get there, that's why I've given you a little bit more information on the pole zero mapping. But now if you had zeros and pole factors for the pole zero mapping, we actually just map those poles at, let's say, S equal minus B. We produce a factor that has a pole at Z equal to E to the minus BT, where the pole was at minus B, S equal minus B. We're simply using this relationship that we should feel comfortable with, Z is equal to E to the ST, in mapping those poles and zeros. The only thing that might be a little bit interesting is where did this Z plus 1 factor come from? And that's due to the number of zeros at infinity in your original transfer function g of s. In g of s here, how many zeros at infinity are there? There's one, and that's because we have a difference in the orders of our denominator and numerator. In this particular case, we have a numerator of order 1, a denominator of order 2, so the zeros at infinity is really equal to the pole 0 excess, or 2 minus 1. And however many of those we have will be mapped then into a factor z plus 1 raised to the power of that pole 0 excess. And last time we talked about infinity in the complex z-plane being equal to z equal to minus 1. And that's because we're walking, instead of walking up the imaginary axis like we do in the s-plane, now we walk around the upper half of the unit circle, and that is how we get our frequency response behavior in the z-domain. And there we only have a finite distance to walk, and when we get over to the other side, we start at dc, which is z equal 1, and then we just start walking along. Different angles correspond to different sort of points on our frequency axis in the z-plane. And when we get all the way over to 180 degrees, or at z equal minus 1, that's really the highest frequency we look at in the sampled space or in the z-plane. That will hopefully become a little bit more clear as we work through it, but I wanted to sort of give you that background before we work through the details. Here's what we're doing in terms of a block diagram. We're now focusing on scenario number 1 in our discrete equivalent. If we have this analog block diagram where we have a analog controller, capital C of S, which if you've had 441, maybe you've seen a particular controller. Maybe it's a phase lead controller, maybe it's a gain, maybe it's a PI controller or PID. If you haven't had 441 or 541, that's fine. We'll figure out how to design controllers after we've gone through or finished exam number 2. That's when we'll start dealing with controller design. Here, what we want to do is simply say, how do we actually replace this analog controller, which might be op amps and resistors and capacitors? How do we replace that with something that we can implement or realize in a digital way, in a computer, in a microcontroller, in a microprocessor? We want to know, how do we come up with this discrete time transfer function if somebody now has given us a C of S? And we've already done this. If I gave you a low-pass filter as, let's say, an H of S, you now know how to find a difference equation to realize that low-pass filter in a discrete time setting. And that's what we want to do now, is we want to replace the controller, capital C of S, with its discrete time equivalent, C of Z. And we're going to work through many different ways of doing that, but the first way that we are going to discuss involves what's called the numerical integration approach. Stated differently or shown differently, now I've simply extracted those blocks by themselves, and now you could think of this capital C of S as being a filter. Maybe it's some fourth order Butterworth filter, and you want to now realize that in a collection of difference equations or in a difference equation formulation. We want to now figure out, if somebody gives you a C of S, how do we produce a C of Z? That's our discrete equivalent. Let's now step through that for these 4 different ways. Numerical integration, we'll look at 3 different approaches. and it'll be clear how those arise as we're going through, and then we'll look at this pole zero mapping where you just take pole factors and zero factors and map those into the z-plane. Let's look at numerical integration. And this is really consistent with what you would think. If this is now our time axis, and let's say that we now have a curve that's described functionally by x of t. That's just some generic waveform. And what we want to do now is worry about the area underneath that curve x of t. Or you could say, oh, let's look at now y of t being this integral from 0 up to some time t of x of tau d tau. Where now we could say, oh, here is t. This value right there will actually be x of t, and we want to know what does this actually look like in terms of y of t. Y of t is that particular area. Y of t is going to be the area under the x of t curve up to time little t. So that's how we're defining y of t, and it's related to x of t, and we want to now know, can we numerically approximate that shaded area? This is really going back to your fundamental calculus as far as how did you find the area under that curve. We're going to try to do it numerically now. If little y of little t is that, what is little y of little t minus capital T? That's the same area under x of t. It just doesn't quite get to little t. It gets to little t minus capital T, or one sample period. If capital T represents a sample period, we're now simply going up to, and I'm going to exaggerate this, let's say this is now t minus capital T. We would just go up to that point, and then we would have this shaded region where the black shaded part is y of t minus capital T. So this y of t minus little t minus capital T is the area under x of t up to time t minus capital T. And now we can relate those two y's to each other. We can say that y of little t is little y of little t minus capital T plus what? How are y of t and y of little t minus capital T related? Can you generate little y of t, which is the blue shaded area, from the black shaded area plus a little bit of an expression? Isn't it just this little sliver that's not cross-hatched? It's just blue shaded. It's not blue and black. We now need to find that area underneath the x of t curve between little t minus capital T and little t, and add that on to y of little t minus capital T. We just want to find the area under that little sliver. Yes, so now this is going to be the integral from little t minus capital T to little t of x of tau d tau. And that's the concept. That's it. And now what we're going to look at is different ways of approximating that integral. And to do that, let's go ahead and in this expression, let's go ahead and dice up or slice up our time axis by letting little t be little n capital T. So that now we have y of little n capital T equaling y of, do you see if I put in little n t for t, I will have n minus 1 capital T plus the integral from nt minus t to nt of x of tau d tau. And the different numerical integration strategies are all based on this approximation of the area in that little sliver. Our different numerical integration techniques are based on how this integral from nt minus t to nt of x of tau d tau how are we actually going to approximate that integral? Can we do the whole thing? Can we go ahead and integrate the whole area? Well, what we're wanting to do is turn this into a difference equation approach. And so we want to say, here's the area up to this time. What's the area that or what do we need to add to that to get to the area one time step into the future? So we're trying to do it iteratively and not do it all at once. And that's what we're trying to do. We're trying to come up with a difference equation based on approximating this integral of x of t, just over that little sliver of time or one sample period in time. And if we go back then here and we replace t with nt, this point becomes x of little n capital T. This point becomes x of n minus 1 capital T. And this point on the time axis is just one sample period to the left or in the past from little n capital T. That's now the labeling that we want to use to try to determine how we are going to go ahead and approximate this piece, which is just that little sliver beyond y, or the area under that curve, up to time, little n minus 1 times capital T. And hopefully these descriptors make sense. Let's call the first one, the first numerical integration approach, a forward rule. And with the forward rule, what we are going to do is we're going to go ahead and approximate this integral, which is just that little sliver's area, with a rectangle, and the rectangular area that we're going to approximate it with is based on the value of x at the previous time step, and we're going to just look forward from that point on. Let me see if I can state that. Approximate the integral with the rectangular area looking forward from x of n minus 1 t. Or if we go back to the picture, we're now approximating this blue shaded area by taking this value and just going over and holding that, looking forward one sample period. This distance is one sample period in width. That rectangular area is then going to be the width, capital T, times the value of our x at time, little n minus 1 times t. In the forward approach, then, we're looking at doing this integral from nt minus t to nt of x of tau d tau. We're approximating that with the rectangle that's given by t, that's the width, times the height, which in this case is the height at time n minus 1 capital T, and we're looking forward in time. And this now allows us to rewrite that difference equation using the forward rule as y of nt is approximately y of n minus 1 t excuse me, plus t times x of n minus 1 t. And that's now our difference equation for this forward rule of numerical integration. What if we transform that time domain equation? What are we going to end up with? What if I transform y of nt? What does that yield in the transform domain or in the frequency domain? Little y of t, now I'm just z transforming it. Or little y of n. I just have to hit the shift key, don't I? That's just a capitalization. Here I now have capital y of z. And I'm going to forget that this is an approximation. I'm just going to say is equal to. And now what happens when I z transform y of n minus 1? So now we have to do this operator of z to the minus 1 times capital Y of z. And what happens now when I z transform the last term in that difference equation? What happens to the capital T? That's just a constant, so that slides right through the z transform. We have t, and then what else? We have a z to the minus 1 times capital X of z. Everybody follow where that comes from the difference equation in the time domain. Now we can actually find a transfer function between the z transform of our waveform x and the area underneath that waveform z transform y. Or we can now say 1 minus z to the minus 1 times y of z is equal to t z to the minus 1 capital X of z. And our transfer function is outputs transform over inputs transform, producing then, by performing the appropriate cross multiplication, numerator is t z to the minus 1 over 1 minus z to the minus 1. And if you're not comfortable looking at that in terms of polynomials of z to the minus 1, we can multiply by 1, which is z over z, and that then produces t over z minus 1. That's now the transfer function associated with a numerical integration forward approach. So what? We want to make this work no matter what kind of transfer function you start with, h of s or any particular c of s. We want to be able to use this result. Let's remind ourselves what happens in the analog or the continuous time case. If we recall, if we have y of t is equal to this integral from 0 to t of x of tau d tau, what happens when we take that into the frequency domain? What if we now Laplace transform this? What happens to lowercase y of t when we go into the frequency domain or the S domain? Again, we just have to do the shift key, don't we, for y of little y of t. This becomes capital Y of s. And what does an integration operation look like in the frequency domain? That's 1 over s. This is now 1 over s times capital X of s. This then has a transfer function of 1 over s. That's what you would expect. The integration operation in the S domain is 1 over s. We now can compare that to what we just found for the Z domain numerical integration approach with the forward approach. So let's now compare those. The comparison then says, oh, we had a 1 over s, and what did that look like in terms of z? This, capital T over z minus 1. We typically don't like to think on our head. We don't maybe like to do headstands. So let's invert that. And what does S then correspond to if we invert the right-hand side? And here is our result. We've now cooked this up, and now it's coming out of the oven, and we've figured out what to do with this forward numerical integration approach. We can now say anytime you give me a transfer function, c of s, and you want the c of z, everywhere I have a s, I just replace it with z minus 1 over t. I'm now going to replace s with this expression, z minus 1 over t, in a given transfer function, h of s, to obtain an h of z. When you're looking at something new, what's maybe something you might want to think about is trying to relate that or connect that with something you already feel pretty good about. What's a transfer function that we've been using throughout the entire course to maybe think that we feel good about it in a filter sort of way? What kind of a filter have we been playing with? A low-pass filter. And let's not get too crazy. Let's just make it first order. So let's now look at a low-pass filter. And see if we can now find its discrete equivalent using this approach, this numerical integration, forward rule based approximation. So now our h of s, what's a first order low pass filter look like? The only thing I would do on that to clean it up is I might do that. Why did I do that? Pardon? So why would I look for a low-pass filter equaling A over S plus A? Let's just analyze what we have for this analog case. Where's the pole? Do you see the Bode plot for this? It would be, well, I'm giving out the answer. What finite, do we have any finite zeros? No, there's no finite value of s that causes that h of s to vanish or to become 0. So we have no finite 0. What's another part or piece of a low-pass filter is maybe the low-frequency gain. What's the DC gain? Where do we evaluate h of s to find the low-frequency gain? When s is equal to 0. That's as low as you can go, right? That's right at the origin in the complex S-plane. If we now plug in s equal to 0 here, that's why I picked A upstairs, because now I have A over A at DC, or I have a DC gain of 1. In the Bode plot, then, I would be 0 dB out to where? Out to a frequency of omega equal to A, and then I would start rolling off. And how fast am I rolling off? In the stop band, minus 20 dB per decade. Let's now use this classic low-pass first-order filter and look at what happens when we apply this numerical integration forward rule to it. We now want to do the forward rule to find a discrete equivalent. And I'm going to go ahead and call that, put as a subscript of F for the forward rule, because we're going to look at different rules to convert from an H of S to a different capital H of Z. The process was to start with H of S, and everywhere we had an S, we would replace it with what we derived the relationship to be, which was this factor z minus 1 over t. So now we had an A, there was no S upstairs, we had one S downstairs, And if we wanted to clean this up a little bit, we might multiply by 1, where my 1 is t over t, and now my discrete equivalent using the forward rule, the numerator is AT. The first factor in the denominator just becomes z minus 1 because I'm multiplying by capital T. And the last term in the denominator is AT. So that now I have this AT over z minus 1 plus AT, and that's supposed to be a low-pass filter in the discrete time setting. This is a discrete time or a z-domain transfer function for a low-pass filter. Does this seem consistent? Oh, let me just say discrete, because I'm still looking at the transfer function. So here's the frequency. Where's the pole? We find it exact the way we always find poles. We just, what values of z cause the denominator to vanish? Does that seem okay? Where is that pole? Is it real? It better be, since it's first order. Hopefully we've stayed on the real line. And where are we? Well, we're just a smidgen inside the unit circle from 1. 1, z equal to 1 is our DC point in the complex z-plane. Like s equals 0 is the DC point in the s domain. So now we've just moved in. So whatever A was, and T, you know how to pick T, that's the sample period, we'll now have 1 minus AT. So if AT, if that product was 0.2, the pole would be at 1 minus 0.2 or 0.8. So it's inside the unit circle, which is good for a filter that's a causal filter. It's now going to be well behaved. Do we have any finite zeros? Are there any finite values of z that cause capital H sub f of z to vanish? No. So that seems to be consistent with what we had in the analog filter. What's the DC gain of this filter? And what value of z do we use to find the DC? I told you, but were we listening? I just told you, where's the point in the z-plane where we would evaluate something to find the DC gain? And if you forget, just go back to z is equal to e to the st, and then you hopefully never will forget what s is. S equal to 0, e to the 0, 1. So our DC gain is going to be, what do we have for a gain value when we evaluate this transfer function at z equal to 1? In our case, it was AT over, we had a z there, minus one plus AT. Again, we have a DC gain of 1. So the question was, they have to have the same gain? No, they don't have to. This is just sort of, do we feel a little bit warm and fuzzy with this result? Did we make a math error? Did we do anything wrong? Or does this seem consistent with what we would expect? And it is consistent with our analog filter. We have a low frequency gain of 1. We have a pole that is real and it's inside the unit circle, and where it's located will depend on how we pick our sample period capital T relative to A. And A influences the bandwidth of our original low-pass filter. That's the first of our numerical integration approximation strategies. Let's look at the next one, which is a backward rule. In this approximation, we're going to approximate the integral with a rectangular area looking backward from x of nt. So if we went back to our original picture, now we would be saying, oh, what we want to do now is approximate this area with a hat determined by that red curve. And you can see it's an approximation. Depending on how x of t is moving around, we are obviously approximating that curve. But if x of t was fairly flat, or if t is not picked very big, that approximation is going to be pretty okay. In this case, now we have the fact that we're going to have this integral from nt minus t to nt of x of tau d tau. That's now approximated by t times x of nt. The width is the sample period. The height of that rectangle is determined by x at the present time nt. So that now y of little nt is approximately y of nt minus t plus t x of nt. And you know the drill. You know the recipe. We're trying to end up baking something and pulling it out of the oven. What we want to do now is put it into the transform this equation. So let's go into the transform domain. Really, you just want to tell your buddies that aren't here that we were getting ready for Pi Day because we were baking tonight, right? So now we're trying to figure out what's going to happen with this backward rule. And there's now what it looks like in the transform case. And if we do the appropriate collection of terms and division, the transfer function will be t over 1 minus c to the minus 1. Or if we write it in terms of polynomials of z, we don't have to change anything that we already know about the analog version. That produces a 1 over s in the frequency domain. We compare that with this, which is tz over z minus 1. And again, we may not want to be standing on our head. So we now say, oh, we can now say S is going to be replaced with Z minus 1 over TZ. In the backward rule, then, we have a little bit different replacement strategy. We now replace S with Z minus 1 over TZ in H of Z, I'm sorry, in H of S, to obtain H of Z. And let's go ahead and look at the low-pass filter again with this different approximation strategy. We'll now use a subscript of B for the backward. Whoops, and it's not H sub B of S, it's H sub B of Z, is found from H of S when S is now replaced everywhere. So if this was a higher order polynomial, numerator and denominator, everywhere we would have an S, we would square it, cube it, but it would be this expression, Z minus 1 over TZ, that would be squared or cubed, etc. So it could get a little bit gnarly in terms of computing, but the concept is not hard. In this case, we're replacing S with Z minus 1 over TZ, or we now have A over Z minus 1 over TZ plus A. Let's clean that up a little bit by multiplying by 1 again, where our 1 is TZ over TZ, and H sub B of Z now becomes a numerator of ATZ, a denominator of Z minus 1 plus ATZ, or combining terms with like powers of Z, we now have this sort of pole zero structure. Did I do the algebra correctly? Where's the pole? Again, we just evaluate the denominator. We set it equal to 0 and we solve for Z. That's going to be Z is equal to 1 over 1 plus AT. A is the distance into the S plane where our pole is, and now where is this pole going to be in the Z plane? What's 1 plus AT? It's a little bigger than 1, is it not? Before, if we said AT was 0.2, this is now 1 divided by 1.2. So where is that? Well, that's close to where we were before. It's still inside the unit circle. This seems okay. Do we have a finite zero? Yes, here we do, don't we? So now we have a finite zero. Where is it? It's now at the origin. How fast is that? So now in the z-plane, you kind of have multiple infinities. Z equal to 0 is pretty quick, is it not? If it was a pole and you had something at z equal to 0, how quickly would it vanish? how many steps? If you now had z, that's our mode. If we had 0 raised to the n, it's going to vanish in one time step, isn't it? That's called a deadbeat response. If we had a pole at the origin, it's lickety-split fast, right? So now we have a 0 at the origin, so that's a fast 0, and that's kind of consistent with not having one in the analog case. What's our DC gain? We find it exactly the same way. We evaluate h sub b of z at z equal to 1. So now we have upstairs, we have AT, and downstairs we have 1 plus AT times 1 minus 1, or again we have a DC gain of 1. Do you see that we have a slightly different transfer function, but it's consistent with being a low-pass filter, and because it's based on a different approximation rule to that sliver. Let's look at one more approximation. And this one is the trapezoid rule. Now what we want to do is approximate the integral, not by looking forward or looking back. We want to actually connect the dots. Now we want to connect the two heights and form a trapezoid so that if it has some movement between there, if our x of t does, we're going to approximate it with a straight line. Instead of a 0 order, we now have a first order. So approximate the integral by a trapezoid. Or we now have this integral from little nt minus t to nt of x of tau d tau, approximated by, and now you just have to remember or derive your formula for the area of a trapezoid. The width is still capital T, but now what do? You could think of it as averaging the two lengths. So we now have x of nt plus x of n minus 1 t over 2. And really, you could think of this as like averaging the forward and the backward rules. So if you didn't feel comfortable with the forward rule or the backward rule, now you can say, well, let me do their average. Maybe you like this one. So this is like averaging F and B, forward and backward. So that now we have y of nt is approximately y of nt minus t plus, let me go ahead and combine my two constants, t over 2, and then I have x of nt plus x of n minus 1 cap t. What's the recipe? Transform this. So let's now transform this, or go into the transform domain. And we now have t over 2. We have 1 plus z to the minus 1 times x of z. where we just have an x of z and then we have a plus z to the minus 1 x of z, and I've just factored that x of z out. If we now solve this for our transfer function, we end up with that. Or if we multiply by z over z, or multiply by 1, we now have a z plus 1 over z minus 1. And you can already kind of see this connection with the continuous, or the analog case. Let's now compare transforms. One over s now is compared with capital T over 2 times z plus 1 over z minus 1. And we probably don't want to be substituting that in everywhere we have an s to the minus 1 or a 1 over s. We probably want to just play with s. And this is now 2 over t times z minus 1. That looks familiar. That was always appearing in all of our relationships. Now we just have a little different denominator. In one we had a z, and in the other one we just had a 1, so it's sort of looking like a combination of the previous two. And in this case then, therefore, we replace s with 2 over t, z minus 1 over z plus 1, in a generic transfer function, capital H of s, to obtain h of z. And there's no need to stop now. We've been doing it for the forward and the backward. We might as well do it for the trapezoid. Or you'll see this may be called the bilinear or the Tuston approximation techniques. So all of those are the same. Here's our trapezoid rule, or bilinear transformation. And we're applying that to our generic first order low pass filter. Subscript now is T for trapezoid. That's H of s, with s now replaced with 2 over t times z plus 1 over z minus 1. Or that's a over s, which was 2 over t, z plus 1, z minus 1, plus a. And if we wanted to, we could multiply that by different things. Suppose we multiply it by t times z minus 1 over t times z minus 1. Question?
Yeah, wasn't the s backwards, like 0 to the minus 1 over 0, and the transfer function?
So now where did I mess up?
Right there, s goes c minus 1 over c.
Thank you. So now this needs to be z minus 1 over z plus 1. I was just making sure you're staying awake. So that needs to be changed here. And now if we multiply this by something like that, we'll end up with AT times z plus 1 over 2 z minus 1 plus AT z plus 1. Here we have a 2 plus AT as a coefficient for z. And we have a plus AT minus 2 for the constant coefficient. Where's our pole? Did I do that right? So it's the negative of AT minus 2, or it's 2 minus AT divided by the coefficient scaling z, which is 2 plus AT. And where's that going to be located? Does it seem okay? What's AT? Something a little bit pretty small. Let's say it's 0.2 again. So now we have 2 minus 0.2, 1.8 divided by 2.2, so it is less than 1. Yay! Right? So it is in the right location. Do we have a finite zero? Where is it? Negative 1. Does that seem okay? That again is fast, isn't it? That's on the unit circle as far away as we can get in the z-plane on the frequency response curve. It's at minus 1. Yes. What do I mean by fast? So those of you that didn't see that, you're lucky. But fast means shaking really, really fast. So in terms of frequency response, if we're on the unit circle, that's how we get our frequency response. Anything on the unit circle gives us this oscillatory behavior. In the z-plane, as far as we can go is only minus 1. And that's actually a frequency equal to half of our sampling frequency. So if we sampled at, let's just say 100 hertz, as fast as we could shake would only be 50 hertz for the discrete time system. But that's really fast, okay? That's as fast as we can go in our discrete time setting. If we put something in faster, what's going to happen? It's going to be aliased, and it's going to look like it's between DC and 50, even though it maybe is bigger than 50. So that's why we have to do anti-aliasing filters. But we haven't gotten there yet. But we do have a 0 at minus 1 in the z-plane. What's the DC gain? And if you're running out of time on the exam, what would you do? I would just say put slash z equal 1. And maybe don't worry about evaluating it. If you're out of time, at least you know, you're demonstrating to me that you know how to calculate that. So I'd only take off about 57 points out of 60 for not evaluating it, but we're all in a good mood, right? We're a few days from spring break. So you know that I was joking on that. But here we would look at z equal to 1, and we might as well compute that for grins here. because I know you'll race home and do it anyway. So I'm going to just beat you to the evaluation. What happens upstairs? What do we have? We have 2AT. Downstairs we have 2 plus AT plus AT minus 2 . So we have TAT divided by TAT giving us 1, which is good. We have a DC gain of 1. Question? So now the question was, what? You didn't see the fast before, did you? So now you have the z-plane, and the question was, I remembered, that was the questioner saying, I remembered something close to the origin being fast. Let's say here's one. Which of these poles is faster? The red pole or the blue pole? Which is faster? Can I ask the opposite? Which one dominates? So I'm asking two different questions, am I not? Which dominates the response? If I had a two-pole system with these two poles, which pole dominates the behavior? The red pole, the one closest to 1. So that means the fast one is the blue pole. It is closer to the origin. So in terms of poles, that's a good thing if you wanted a faster pole. The blue is faster. Whoops. And this is slow or dominant. Now what I'm introducing, a new curve to this, is I'm saying, oh, we're over here at -1, but now I'm assuming that we are interested in the frequency response, which is when we now walk around this unit circle from 1 to -1. And as we do, we get higher and higher in frequency as we walk around. At z equal to 1, we're at DC, and we go all the way to -1. We are now up to omega sub s over 2 in terms of frequency, the Nyquist frequency. And so you could think of that as being fast in a frequency sense. If you're now shaking this system is only really going to shake at that high frequency, omega sub s over 2. So you kind of have two different fasts to think about in the z-plane. And I wouldn't try to make one absolute and the other one dismiss it. You just kind of have to keep those two things clear in your head. Do you see why I'm saying -1 can be viewed as fast and 0 can be viewed as fast? We're actually going to learn that we probably don't want poles between 0 and -1. Those kind of give us nasty behavior. They're stable, but they kind of give us weird behavior. Now, what I want to do is, before we get too far off, and did that help answer your question as far as fast? And then you didn't have to worry about seeing what you missed before, right? But what I want to do is very quickly talk about, and we'll do this a little bit more when we get back from spring break, but I'm sure you want to go home and do all of your homework, maybe even tonight or maybe Friday night, sometime between now and when we meet again, so I want to give you some material. This is now called pole zero mapping or pole zero matching, but this is another discrete equivalent approach. And what the idea here is that one, you map poles of H of S to poles of H of Z. And again, we're using this relationship. Z is equal to e to the st. So if you had H of S that was 1 over S plus A, this has a pole at minus A. You would use that information to inform the factor, the pole factor in H of Z. You would now say, oh, my pole is going to be at e to the minus at, so that the pole factor looks like that. And maybe what I should have done is not worry about what's going on upstairs, because we'll have to worry about matching gains to be consistent. But do you see the idea? And if we had a finite zero, we would do exactly the same thing. We would map it through z is equal to e to the st. So here we map zeros of H of S to zeros of H of Z. And that's sort of the caveat. If we have zeros at infinity in the analog case, we introduce a factor z plus 1. This gets back to your earlier question about what's fast. Well, this becomes a very fast zero, because z equal to minus 1 causes that factor to vanish. So you can think of that as being a zero at infinity in the z-plane. But finite zeros map consistently with how we just showed the factor in for the poles. The other step in this process is then to match gains of H of S and H of Z. Meaning if I had a low-pass type filter, then I might want to match gains at DC, which means that I would be comparing. So let's now say low frequency. You might have H of S evaluated at S equal to 0 being equal to something. In our previous example, it was 1. And we would then have an unknown gain K in our H of Z, but we would solve for that unknown gain K such that we would get equality at low frequency or at DC. If our filter or our circuit or our system was more high pass in quality or characteristic, then we might map this or match these gains at high frequency. So we might let S go off to infinity, and what we want Z to go to? We might want it to go to probably Z equal to minus 1, maybe. Because we've learned that there's kind of two different fasts in the Z-plane. And it may vary as far as where you want it to do, or what you want it, how you want it to behave. But you can now match the gains. Is it clear how to maybe get started on your homework problem that deals with pole zero mapping? It's not a challenging concept. The only thing that might throw a wrinkle in is this concept of infinite zeros. And That just says include a factor, z plus 1, with the amount of factors consistent with how many zeros you have at infinity. The exam is up to here, and we'll go through the pole zero mapping when you come back from spring break. In a little bit more detail is the plan. Okay, so enjoy your break, and we will see you in a little over a week.